Hi, welcome to the fifth lecture of General Chemistry. This lecture we're going to be covering material from Chapter 11, and that is specifically valence bond and molecular orbital theories. Now, valence bond theory builds off of Vesper theory, material we were talking about in Chapter 10, and then molecular orbital theory is a little bit different. On its own, and we'll be covering that in the second half of the lecture. Let's start with some review questions over Chapter 10 material. Review question 1. Identify the best structures for cyanate, which is NCO-, and fulminate, CNO-. To answer this question, the structures are already drawn for us. It might help you to put in the unpaired electrons. So I'm just going to draw those in here. So when nitrogen has a triple bond, there will be one lone pair. When there's a double bond, it will have two lone pairs. And then we'll include them for oxygen as well. And we'll do the same for the other structure. Okay, now to answer this question, we'll have to do formal charges for the atoms in these structures. So we really only have two structures for the cyanate ion. And then when we calculate the formal charges, this top structure shown in A, the nitrogen will have a formal charge of 0, carbon will be 0, oxygen will be -1. And the structure shown in B will have nitrogen with a -1 formal charge, carbon 0, and oxygen 0. So with this, choosing between those two, which would you pick? You want the negative formal charges on the most electronegative element, and that would be oxygen. So the best choice would be A, and that's the same as in C and D. Okay, now we're going to need to look at the fulminate ion. So the top structure, carbon will have a -2 formal charge, nitrogen a +1, oxygen 0. That's the same structure as shown in B, but we know B is not a good choice because the structure of cyanate is not as good as in the other choices. So we can eliminate that choice. Let's look at the structure in C. Formal charge on carbon would be a -1, nitrogen would be a +1, and oxygen a -1. And the final structure, carbon in this structure is a -2 formal charge, nitrogen a +1, and oxygen a +1. So if we have to pick between A, C, and D, which one is the best choice? Well, we can eliminate A and D, and that is based on the fact that there is a formal charge of 2, -2. And both times it occurs on carbon, which in this case is the least electronegative element in the molecules. So our best choice for the structure for fulminate would be structure C, where carbon has a -1 formal charge, and oxygen has a -1 formal charge. Okay, review question 2, and hopefully this one should be fairly easy. Which compound listed below is represented by this picture? And what you'll notice is the molecule in the picture is a linear molecule. It has a linear molecular geometry. So select the formula below that gives a molecule with a linear molecular geometry. So if we draw the Lewis structures, you should come up with a structure like this for NO2 minus. And what formula can we write for that? That would be an AX2E1. So that is not a linear molecule. It's actually bent. Let's look at SCl2. And this molecule is AX2E2. So tetrahedral electron geometry and a bent molecular geometry. Now on to CO2. CO2 is actually linear, AX2, which matches our picture. Just for completeness, we'll look at SO2. And SO2 has a structure like this. Again, it's an AX2E. So trigonoplanar electron geometry, which would lead to a bent molecular geometry. Finally, question 3. Which of the following is true of the bond angle, theta 1, in BrF2 plus, compared to the bond angle theta 2 in ICl2 minus? First step, we need to do the Lewis structures. So BrF2 plus. There'll be 20 electrons total. Bromine will be in the center because it's less electronegative than fluorine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have 4 electrons that are in bonds, so we use 16. We have 4 left, so we'll put them on bromine. And we get this structure. So this is AX2E2. That will give a bent molecular geometry. So theta 1 will be less than 109.5 degrees. Remember that 109.5 degrees would be a tetrahedral geometry, but since we have 2 lone pairs, the angle is going to be slightly less because the lone pair, they give greater repulsion. Let's look at ICl2 minus. For this molecule, because we have the minus charge, we're actually going to have 22 electrons to work with. And it's going to be the same basic pattern as the molecule above, but now we have 2 extra electrons. So they go on the iodine. And remember, iodine is third row of the periodic table or lower, and it's bonded to chlorine, which is a very electronegative atom. So when things are bonded to fluorine, chlorine, or oxygen, they can have expanded valence. And that's what this molecule has. So the formula for this molecule would be AX2E3. And what would the molecular geometry be? Well, that's linear. So theta 2 is going to be 180 degrees. So if we look at the angle theta 1 and theta 2, what can we say? Well, theta 2 has to be bigger than theta 1. And is that a choice? Yes, that would be choice C. Theta 1 is smaller than theta 2. Right. Moving on to chapter 11. 11.1, we're going to introduce valence bond theory. And 11.2, we're going to talk about the types of orbital overlap and covalent bonds that they form in valence bond theory. So what is valence bond theory? Well, it's a theory where of covalent bonding, and specifically what valence bond theory states is a covalent bond forms when orbitals of two atoms overlap and a pair of electrons occupy this overlapping region. The space formed by the overlapping orbitals can accommodate a maximum of 2 electrons, and these electrons must have opposite signs, so they must be paired electrons. The greater the overlap of the orbitals, the stronger the bond. And the extent of this orbital overlap depends on the orbital shape and the orbital direction. So let's see an example. The simplest example, the simplest molecule we can come up with would be H2. And on the left we see the atomic orbitals for both hydrogen atoms. They're 1s orbitals. Each has 1 electron. Now they can come closer to form a bond, and in valence bond theory we show that as the 2 orbitals overlapping. So we have this region here where the orbitals are overlapping each other, and they're sharing their 2 electrons, and they're oppositely paired. Okay. So we can also have orbital overlap with p orbitals, and that's shown in this figure, where hydrogen, the 1s orbital of hydrogen, is overlapping with the 2p orbital of fluorine. Again, in the overlap region, they share electrons, and the electrons are opposite spin. We can also have a bond forming between 2 p orbitals, and that is shown here on the right. So for a F2 molecule, we have an overlapping region of the p orbitals, and you'll notice now that these are the px orbitals. So the px orbitals can overlap with one another, but if you notice the pz orbital or the py orbital, they're not going to be able to overlap with the px orbital to form a bond. And that, again, is one of the stipulations. The orbitals have to be correct shape, and they have to be in the correct orientation to form overlap with one another. So valence bond theory and orbital hybridization, which we're going to talk about, was developed by Linus Pauling. And we've mentioned him before when we were talking about electronegativity. But Linus Pauling was really a pioneer of valence bond theory as well. So the orbitals that form when bonding occurs are different from the orbitals in isolated atoms. And that's important to remember. That's the basis of valence bond theory, is that the atomic orbitals, when an atom is by itself, are different than the orbitals an atom uses when it makes bonds in a molecule. So the atomic orbitals hybridize into molecular orbitals. And if they didn't do this, we could not account for the molecular shapes that we observe. If we just tried to use atomic orbitals, s orbitals and p orbitals, we couldn't come up with the molecular shapes that are observed. And a classic example for this would be methane, CH4, with the tetrahedral geometry. There simply is no way to make tetrahedral geometry if you're using an s atomic orbital and 3p atomic orbitals. And I'll go through that example on the board in class just to show. But if you want to sort of think about that yourself ahead of time, it's a very good example of why there needed to be a valence bond theory to explain molecular shapes. So these atomic, in valence bond theory, we say atomic orbitals mix or hybridize when the bonding occurs, and this forms hybrid orbitals. And the spatial orientation of these hybrid orbitals really explains molecular shapes that we observe. So what are some features of hybrid orbitals? Well, the number of hybrid orbitals formed equals the number of atomic orbitals that are mixed. And a very big hint that I think when you're asked about what hybrid orbitals form, just remember that the atomic orbitals used in the hybrid equals the steric number of that atom in a molecule. The type of hybrid orbitals formed varies with the types of the atomic orbitals that are mixed. The shape and orientation of hybrid orbital maximizes overlap with the other atom in the bond. So figure 11.3 in your book, this gives a picture of what it means when an orbital is hybridized. In this case, we have a 2s orbital and a 2p orbital, atomic orbitals mixing, and they form what's known as an sp orbital. And this is really sort of a accurate view on what these orbitals look like. But if we want to draw this by hand, a simpler way to show this would be here at the left, and these would be two sp orbitals, and you'll notice that they form a linear geometry, and it sort of looks like a p orbital, a p atomic orbital, but the heads are a little bit flattened out. And let's look at an example of this. If we had a beryllium atom, it would take, and these are our atomic orbitals, 2s and the 3 2p orbitals. If we took a 2p and a 2s orbital to hybridize them, our new orbital energy diagram would look like this. We'd have two sp hybrid orbitals and two p unhybridized orbitals remaining. And notice also, when we mix two orbitals, the energy level is somewhere in the middle. So it's higher energy than the 2s orbital, but lower energy than the 2p atomic orbital. Beryllium would have start with 2 electrons in the atomic orbital, the 2s atomic orbital. Now it'll, because of Hund's rule, 1 electron would go into each sp hybridized orbital. So here's a 3-dimensional picture we have the spherical s orbital and the p orbital. When they mix, they form sp orbitals, which each of them look like a half of a lobe of a p orbital, but just a little bit flatter at the tip. And when it forms a bond, we see it can form a bond with two chlorine atoms. The overlap would be the sp overlapping with the p orbital from chlorine. And we'll see the linear molecule it would form down here on the left. And you'll also notice we have unhybridized p atomic orbitals still on beryllium, but they don't have any electrons in them. All right, let's look at the next element in the periodic table. That would be boron. Boron has 3 electrons. It can form 3 hybridized orbitals. It will use a 2s atomic orbital and 2p atomic orbitals. And now we have 3 identical hybrid orbitals that are labeled sp2. So that's a thing I should point out right now, that if you have 3 identical orbitals, you get one from the s, one from the p, and another one from the p. So that becomes sp2. So you add the number of atomic orbitals up, and that has to equal the number of hybridized orbitals you form. And that makes it really easy when you're looking at a molecule, say that forms three bonds. You need 3 hybridized orbitals. You get 1 from the s, and then 2 from the p. And that's how you can count up the atomic orbitals that are used in the hybridized orbitals. And again, there's 1 electron in each hybridized orbital because of the way we fill orbital diagrams, Hund's rule. Here's the 3-dimensional picture of a molecule that boron will form, boron trifluoride. And now you see that we have, in orange, the 3 identical sp2 orbitals, and they interact with p orbitals on the fluorine, and you see that now there's 2 electrons that are shared, and they have paired spins. The sp2 orbitals, they form a trigonal pyramidal geometry. There's 3 of them, and Vesper theory states that they want to repel each other, get as far away from each other as they can, and that would be trigonal planar geometry. If we go up again, so now we have a steric number of 4. We're going to need 4 identical hybrid orbitals. Where do we get them from? We have 1 s, and now we have 3 p orbitals, so that becomes sp3 hybridized orbitals. And an example, a good example of sp3 hybridization comes from carbon. And a 3-dimensional picture of methane is shown below. Now we have 4 identical sp3 orbitals. They're in a tetrahedral geometry, and they're overlapping with the 1s orbital of hydrogen, and there are 2 electrons shared in each overlap. Another example of an sp3 hybridized orbital would be NH3. Now nitrogen, the nitrogen atom, has 1 more electron than carbon. So we start with 5 valence electrons. When we fill the hybridized orbitals now, we're going to get one that is filled. And what that becomes is this lone pair that's on NH3. So 3 of the sp3 hybridized orbitals go to form bonds with hydrogen. The other one is already filled, and it is a lone pair. And this will end up giving us a trigonal pyramidal molecular geometry. And now if we add another electron, so if we look at oxygen now, it has 6 valence electrons. So 2 of its sp3 hybridized orbitals are now filled. And that is shown here on a water molecule, a model of water molecule. And we have 2 lone pair electrons on oxygen. Again, they're in the sp3 hybridized orbitals. So there are 4 identical sp3 hybrid orbitals. 2 are being used as lone pairs, 2 are bonding to hydrogen. If we move up to a steric number of 5 now, we can only have a possible 4 hybrid orbitals when we use s and the p orbitals, right? Because there's 1 s and 3 p orbitals. So if we have a steric number of 5, we need another orbital to mix, to hybridize. And we get that from the d orbitals. So for a steric number of 5, the hybridization would be sp3d. You have 1 from the s, plus 3 from the p, plus 1 from the d, and that will give us a steric number of 5. So if we look at phosphorus pentachloride, the central phosphorus atom now, it has 5 valence electrons, 2 in the 3s, and then 1 each in the 3p. But if we're forming a molecule with the steric number of 5, we need to add 1 of the 3 d orbitals. When these mix, they make 5 identical sp3d hybrid orbitals, shown here. And the 5 valence electrons from phosphorus, 1 each goes into the new 5 hybrid orbitals. And then these hybrid orbitals can form bonds with the p orbitals on chlorine. So we get 5 identical hybrid orbitals forming 5 identical bonds. And this gives us a molecular geometry known as trigonal bipyramidal. So we take this a step further for a steric number of 6, and as you guessed it, now we're using 1 more d orbital. So we have 1 from the s, 3 from the p, and 2 from the d to give us our steric number of 6. So this is called an sp3d2. Our example for a steric number of 6, classic example would be sulfur hexafluoride. Sulfur comes with 6 valence electrons, and that is good to put 1 in each of the 6 sp3d2 hybrid orbitals that are formed. And this molecule forms what's known as an octahedral molecular geometry. Here's a good table, table 11.1, that summarizes this. If you have a linear geometry, you have 1s and 1p that are mixed, and there's a typo here, so that forms 2 sp orbitals, and you have 2 remaining p orbitals that are unhybridized. Again, if you have trigonal planar geometry, you need 1s, 2p, that makes 3 sp2 orbitals, and there's 1 unhybridized p orbital remaining. For tetrahedral, you have 1s, 3p. What does that make? That makes 4 equal sp3 orbitals. And you have no unhybridized orbitals remaining. For trigonal bipyramidal, 1s, 3p, 1d. That gives you 5 equal sp3d orbitals. There's 4 d orbitals that remain unhybridized. For octahedral geometries, just adding 1 more d orbital. So you have 1s, 3p, 2d. That gives 6 equivalent sp3d squared, d2 hybridized orbitals. And again, you have the remainder of your d orbitals, 3 of them, that are unhybridized. Here's another figure that I like this figure just a little bit better. It tells you the hybridization here, gives you the orientation of your orbitals, and the yellow orbitals are your hybrid orbitals, and it shows the unhybridized orbitals in blue. So I think this is a good picture if you want to see the hybrid and unhybridized orbitals together. And this is another important column. It tells you the number of bonds that you can form with this hybridization. So if we let's look at an sp3 hybridized orbital, and we have 2 bonds. So what would that be? The formula of that molecule would be AX2E2. So what was the molecular geometry for that? That would be bent. Another column that you could add to this figure would be steric number. So if your steric number is 2, you'd have sp hybridized orbitals. The steric number of 3, you'd have sp2 hybridized orbitals, and so on. And this is a continuation of a figure we showed in chapter 10, steps to get molecular shape. You start with molecular formula, then you follow the steps to get the Lewis structure. From the Lewis structure, you can get a molecular shape and electron group arrangements. And finally, last step in this, you use the table, a table like we just showed the previous 2 slides, and you determine the hybridization of an atom in that molecule. So there are some limitations to this, the valence bond theory. And one of them is that the hybridization is not always consistent with observed molecular shapes. And this is really the case in larger atoms. And an example of this would be sulfur in H2S. The bond angle is approximately 92 degrees. And this is really closer to the angle that would be between unhybridized p orbitals than is predicted by the tetrahedral hybridized sp3 orbitals. But in any case, in molecules we look at in this class, we're going to assume that valence bond theory works. It really does give a very good approximation, especially for the types of molecules we talk about in a general chemistry class. All right, let's try some practice questions. What's the hybridization of xenon in xenon tetrafluoride? First step, we need to come up with the Lewis structure. So let's count electrons. Xenon has 8 valence electrons. Fluorine, they have 7 each, and there are 4 fluorine atoms in the molecule. So that gives us 28 plus 8, which would be 36 total electrons. Xenon will go in the center. It is a noble gas, but it is so far down the periodic table that it can actually, in certain circumstances, form bonds, especially with fluorine, which is the most electronegative element. Okay, we've used 8 electrons in bonding. And when we add the valence electrons on fluorine, we've used a total of 32 electrons. So we have 4 more electrons, and we need to place those on the center atom, xenon. And xenon, again, it's so far down the periodic table that it can expand a valence. This would be an AX4E2 configuration. The steric number is 6. So what is the hybridization that this molecule requires on xenon? So you need 6 equivalent hybrid orbitals, again because it's AX4E2, steric number is 6. So we get 1 from the s orbital, s atomic orbital. We have 3 atomic p orbitals. That gives us a total of 4. We need 2 more. So those are going to come from the d orbitals. And that would be sp3d2, and that is choice D. Okay, next question. What is the hybridization of each carbon atom in acetic acid? And we'll call this carbon 1 and carbon 2. So take a couple minutes and try to answer this question. So if we first look at carbon 1, how many bonds does this carbon form? It forms 4. There's no lone pairs. So its steric number is 4. So we need 4 equivalent hybrid orbitals. 1 from the s atomic orbital, and 3 from the p atomic orbital. So this is sp3 hybridized. Now for carbon 2, it has a total of 4 bonds, but one is a double bond. So it's bonded to 3 other atoms, and it has no lone pairs. So this steric number is 3. With a steric number of 3, we need 3 atomic orbitals to hybridize, 1 from the s, and now just 2 from the p. So this is sp2 hybridized. And this choice, sp3, sp2, would be choice C. So now that we've introduced valence bond theory, section 11.2, we're going to talk about the types of orbital overlap that we can have, and then what types of covalent bonds those overlaps form. So there are 2 types of covalent bonds. One is a sigma bond, and that's given by the Greek letter sigma. And this bond is formed by end-to-end overlap of orbitals. Another thing to remember, all single bonds are sigma bonds. The second type of bond is a pi bond, and that's given by the Greek letter pi. And this bond is formed by sideways overlap of orbitals. A pi bond is always weaker than a sigma bond because the sideways overlap is less effective than end-to-end overlap. But in a double bond, you first have to have one sigma bond before you can get the second pi bond in the double bond. Let's look at some hydrocarbons to illustrate the different types of bonding. So for ethane, C2H6, the Lewis structure for that molecule is shown here on the left. And you'll notice that all these bonds are single bonds. We can look at the Vesper model, and we get something that looks like what's shown down here. And we can draw now a valence bond theory model where we, instead of sticks for bonds, we show the actual orbital shapes and their overlap. So each carbon is sp3 hybridized. They each have 4 bonds. They're each bonded to 4 other atoms, so they need 4 equivalent sp3 hybrid orbitals. So when we show a sigma bond, we show 2 sp3 orbitals overlapping as such, and then we label that with the sigma, indicating that that is a sigma bond. And you can also show the overlap of a sp3 hybridized orbital with a 1s orbital in hydrogen, and again we label that as a sigma bond. Those are end-to-end overlap. So a sigma bond is cylindrically symmetrical, and the highest electron density is along the bond axis. So that's another important thing to remember about a sigma bond. Cylindrically symmetrical, and highest electron density is along the bond axis. So let's look at ethene this time, when we remove 2 hydrogen atoms and a double bond, carbon-carbon double bond is now formed. So our Vesper picture of the molecule would look like this. And you'll notice that both carbons now have a steric number of 3, so they're going to be sp2 hybridized orbitals. So we have 2 sp2 orbitals come together to make a sigma bond. And you'll notice now we have unhybridized 2 p orbitals remaining on the carbon atoms. And these unhybridized orbitals are what can come together and form the pi bond. And that's shown down here on the left. We see the 2 2p orbitals, and when they interact to form an overlap, you get something that looks like this, and that we label as a pi bond. And a pi bond has 2 regions of electron density. One's above the bond axis and one's below the bond axis. So it has very little electron density in the bond axis, but above and below the bond axis is where the electron density is in a pi bond. And if you were trying to draw this on a piece of paper or something, this picture here is kind of hard to draw. So I would just draw it as lines between the 2 p orbitals, and you can label that as a pi bond. And I'll be sure and draw examples of these on the board to give a better illustration of how you would actually draw a valence bond model. Finally, let's take it a step further, remove 2 more hydrogens, and add another bond. So now we have a carbon-carbon triple bond, and this is ethene. And the Vesper model shown up here, Lewis structure and Vesper model, they're the same now because it's a linear molecule. And the carbons are going to be steric number of 2, so their hybridization is sp. So we see that each carbon has 2 hybridized sp orbitals, and they have 2 unhybridized p orbitals remaining. So the sp and sp can overlap to form our sigma bond, and then we get overlap between one set of 2 p orbitals, so that would be the 2pz orbital, and let's just call this 2py. Those can also overlap. And we see that picture here. This overlap of 2 sets of unhybridized p orbitals gives us 2 pi bonds. So a triple bond is 1 sigma bond and 2 pi bonds. Your book really likes to show these electron density maps, and if we look at the electron density maps for ethane, ethene, and ethine, we see that in each of them there's increased electron density between the 2 carbon nuclei. I should mention a double bond is a little bit less than twice as strong as a single bond, and that's because a pi bond, again, is weaker than a sigma bond. And that's because the overlap, it's not as efficient. The side-to-side overlap is not as efficient as the straight-on overlap. But if we talk about bond order, single bond, a sigma bond, has a bond order of 1. Now, a double bond order is 2, triple bond order of 3. So the bond orders are exactly, double bond has double the bond order of a single bond, but if we're looking at the exact strength of a bond, the bond energy, it's less than twice as strong. So let's try a practice. This practice comes from your book, 11.2, sample problem. So describe the types of bonds and orbitals in acetone. CH3,2CO. So the first step of this is going to be drawing the Lewis structure. So take a few minutes and try working out this sample problem. Okay, the Lewis structure, or in this case, it's more the Vesper structure because we're showing some three-dimensional character with the tetrahedral geometries on these 2 carbons. Okay, this would be the structure we should come up with. These carbons are sp3 hybridized. They have a steric number of 4. The center carbon now has a steric number of 3, so it's sp2 hybridized. And we can also look, if we want to look at oxygen, it's sp2 hybridized as well. That's because it has a steric number of 3. It has it's bonded to 1 carbon, and it has 2 sets of lone pairs. So now if we wanted to draw the valence bond model of this, start with the center carbon. It's sp2 hybridized. So it has 3 equivalent sp2 orbitals. And it also has one unhybridized p orbital. Oxygen will be the same. It has 3 sp2 orbitals. this overlap to form a sigma bond. The two top sp2 orbitals would have the lone pair, and it again is going to have one unhybridized p orbital that can form a pi bond. Now I'll just draw one of the carbons, the methyl groups. There's 4 equivalent orbitals, so that'd be an sp3 overlapping with an sp2, forming a sigma bond. You have 3 more sp3 orbitals, and they overlap with the s orbital of a hydrogen to form a sigma bond. So again, I'll try to draw one of these on the board. Maybe it's probably a little bit easier to see on the board than me trying to scribble something out here on the screen. But that would be the basic way to draw a Vesper, or excuse me, a valence bond model. Okay, next practice question. In CO2, chemical bonding is best described in terms of A, 1 sigma bond and 3 pi bonds, B, 2 sigma bonds and 2 pi bonds, C, 3 sigma bonds and 1 pi bond, or D, 4 sigma bonds. So take a couple minutes and answer this question. Our first step, as always, is to draw Lewis structure. So for CO2, we've drawn this one out quite a bit. So we end up with this structure. The oxygens have a steric number of 3. They are AXE2. So they're going to be sp2 hybridized. Carbon is AX2, so it's going to be sp hybridized. Steric number is 2. So now, what types of bonds do these have? Well, you can see that the carbon, there's 2 double bonds. So if you remember, a double bond is 1 sigma bond and 1 pi bond. Now there are 2 of them, so we can say 2 sigma and 2 pi, if you just want to remember that. Or you can actually draw out this model. Where you have carbon with 2 sp orbitals. Oxygen will have 3 sp2 orbitals. Create a sigma bond. There's 1 unhybridized p orbital on oxygen. Carbon now will have 2 unhybridized p orbitals. Sorry, that's a sigma. So one of the unhybridized p orbitals on carbon will form a pi bond with the oxygen on the right. These are lone pairs. Now the oxygen on the left is the same pattern. The sigma bond there, but its unhybridized p orbital now is going to be 90 degrees different from the other oxygen. So it'll form pi orbital, pi bond, and again it has the 2 lone pair. So that's 2 sigma bonds here and here, and 2 pi bonds, which would be choice B. Now, pi bonds, sigma bond is cylindrically symmetrical. So what that means is there can be rotation in a sigma bond. But that's different than a pi bond. A pi bond has restricted rotation because there's no electron density along the bond axis. It's above and below. And what that does, it can lead to what's known as isomers. So we see that the top molecule and the bottom molecule have the same exact chemical formula. But the way they're arranged is different. On top, the chlorine are on the same side of the molecule. So if you want to draw this as a Lewis structure, the chlorine would be on the same side of the molecule, and the molecule on the bottom, the chlorine, are going to be opposite. And this is what's known as cis, being on the same side, and trans, being on opposite sides. And it's not really important in this class, but if you go on to organic chemistry, this becomes extremely important to know. All right, that finishes up our valence bond theory. Now we're going to discuss a different theory, molecular orbital theory. So there are, as we've seen, problems with some of the bonding theories. For Lewis structures, they give the correct bonding capacities of elements, but they don't account for molecular shapes. So we talked about that last lecture. Now we introduced Vesper in chapter 10, and we talked about valence bond theory, which really builds off of Vesper in this lecture. So these are good. They account for molecular geometries, but one of the drawbacks is that they don't account for magnetic properties, so the electron pairing in molecules. And an example of this is O2. Oxygen, molecular oxygen, O2, is attracted to a magnetic field. And what that means, it's paramagnetic. It has unpaired electrons. And N2, nitrogen gas, is repelled. So it's what's known as diamagnetic. All electrons are paired in N2. But using valence bond Vesper theories, we have no way to account for that observation. Another problem with Vesper and valence bond is they don't account for molecular spectra. And we talked a little bit about atomic spectra. Molecular spectra are really very similar in concept. You have absorption of energy, where electrons can move from a lower energy state to a higher energy state, and then they can drop back down from a higher energy state to a lower energy state as well. And Vesper valence bond do not account for that. So let's look at O2. It's paramagnetic. So atoms or molecules having unpaired electrons are considered to be paramagnetic, and they're attracted to magnetic fields. The opposite of this is diamagnetism, and that's atoms or molecules having all paired electrons, and these are not attracted by magnetic fields. And as we've discussed, O2 is an example of a paramagnetic molecule. N2 is an example of a diamagnetic molecule. So valence bond theory doesn't explain this. That's where this new theory, molecular orbital theory, actually does a very good job at explaining these characteristics, the magnetic characteristics of molecules. And another thing molecular orbital theory is very good at is explaining molecular spectra. If you remember from the Chapter 7 material, we showed atomic spectra. So this would be atomic absorption spectra. Well, you can actually also have molecular absorption spectra, and this is the molecular absorption spectra for H2O. And we're going to talk at the end of this lecture about just what causes the molecular absorption. And we're going to use molecular orbital theory to explain this. Molecular orbital theory was developed really just after valence bond theory, and it was developed by a lot of very important people in quantum mechanics, and you should recognize this name, Hund. That's the Hund from Hund's rule. And what what molecular orbital theory is an addition of atomic orbital wave functions are combined to create what are known as molecular orbitals. So you have atomic orbitals coming together to create molecular orbitals. And in one sense, it is very that aspect of it is very similar to valence bond. In valence bond theory, you had atomic orbitals mixing to form hybrid valence bond orbitals. This is a little bit different in that we're using wave functions of the atomic orbitals are being combined to create molecular orbitals. So it's very math based. We're not going to be talking about the math at all when we talk about molecular orbital theory. So don't get worried about that. But it is very, very heavily math-based. Another important thing to point out is that the molecular orbitals are spread out over the entire molecule. In valence bond theories, your hybrid orbitals are really localized on each atom. But in molecular orbital theory, the new molecular orbitals spread out over the entire molecule. The guidelines for creating molecular orbitals are listed here. So the first guideline, the total number of molecular orbitals formed has to equal the number of atomic orbitals that are used in the mixing process. And that's very similar to valence bond theory. The number of atomic orbitals equals the number of hybridized orbitals. So this is really the same rule. The number of atomic orbitals that are mixed equals the number of molecular orbitals that are formed. And orbitals with a similar energy and a similar shape mix more effectively than orbitals that are different energies or different shapes. Orbitals of different principal quantum numbers have different sizes and different energies, and this really results in less effective mixing. A molecular orbital can accommodate only 2 electrons with opposite spins. Right? This is the Pauli exclusion principle. And electrons are placed in molecular orbital diagrams according to Aufbau's principle, lowest energy orbital first, and Hund's rule that when you have orbitals of the same energy, you first pair electrons unpaired until all orbitals have 1 electron, and then you start pairing the electrons. There are two main types of molecular orbitals that we're going to be talking about, and that's bonding orbitals and anti-bonding orbitals. So a bonding orbital, they hold atoms together. How? They do this by increasing electron density between nuclear centers. They're lower in energy. A bonding orbital, a molecular bonding orbital, is lower in energy than the atomic orbitals from which they formed. The opposite of this is an anti-bonding orbital, and these destabilize the molecule because they don't increase electron density between the nuclear centers. And they actually create a node between the two centers. Now, an anti-bonding molecular orbital is higher in energy and thus less stable than the atomic orbitals from which they are formed. Now, figure 11.5 shows you what using light waves as an analogy to show you what this would mean. A bonding orbital, the waves would reinforce one another, and you'd get an increase in density between the two nuclei. If the waves cancel each other, you have a region between the two nuclei of zero electron density, or also you could call this a node. And bonding in molecular orbital theory is the same as in valence bond theory. You can have two types of bonds, a sigma bond and a pi bond. Now, a sigma bond is a bond with the highest electron density along the bond axis. We've talked about that in valence bond theory. And a pi bond is formed by mixing of atomic orbitals that are not oriented along the bonding axis. So they give the highest density above and below the bonding axis. And what does a picture of these look like? So if we look again at the simplest molecule, we can make H2. Each hydrogen atom starts with a 1s orbital. Now when we add them to form molecular orbitals, we can have a bonding molecular orbital, and that's shown below on the left. And the orbitals mix, and they form the bonding molecular orbital, where you have electron density along the bond axis. Now, we're starting with two atomic orbitals, so we need to make two molecular orbitals. We have the bonding, but we also make an anti-bonding. And that's shown up here, where you have the electron density actually is zero between the two nuclei, and you get a node. A bonding molecular orbital, this case it would be a sigma bond because the density is along the bond axis. That would be written as sigma, and 1s because it uses 1s atomic orbitals to form. And the way you show to label an anti-bonding molecular orbital is you add a star. So sigma star would be the anti-bonding orbital. And also it's important to point out that the bonding orbital is lower in energy than the two atomic orbitals, and the anti-bonding orbital is higher in energy. If now we look at the p, 2p atomic orbitals, they can hybridize. So if py and py interact, you'll notice that they're not end to end, so their interaction is going to be side to side. So what that forms is a pi bond. So their density is going to be highest above and below the bonding axis. And the pi anti-bonding is generally shown something like this. You have a node between the two nuclei, and you can also show this by doing a plus minus, where the nodes, they don't line up. You can show them as pluses and minuses, or you can also do a color. So you can have one colored in solid, matching up with the node that's not colored in, and then the same on the bottom, to show that they're not aligning correctly to form a bond. Now if we look at the 2p x orbitals, atomic orbitals, they do have an end-to-end interaction. So the bonding orbital, molecular orbital, would look something like this. Again, that density is along the bonding axis, so it's going to be a sigma bond. And we call this molecular orbital sigma 2p. And again, the opposite, the anti-bonding orbital that would form from these two atomic orbitals would look like this top picture, where you could show the failure to interact, something like this. They're out of phase, and that is the sigma star 2p molecular orbital. Now, I think it's easier to look at in color. Here is a good picture that shows all the molecular orbitals that we're going to be concerned with. So we have the interaction of s orbitals and p orbitals. We see that the sigma is an oval shape, electron density along the bond axis. You can show the sigma star as something like this, where you have the two orbitals are different color, they're out of phase, and that creates a node. The pi orbital, pi molecular orbital, bonding orbital, you can show like this, where you have the same color on top and the same color on bottom, and this forms a pi bond. And then we have the px end-on-end overlap, and that forms the sigma 2p orbital. And then the anti-bonding orbitals for the p or p atomic orbitals are shown above. And again, you can use pluses and minuses to show they're out of phase, or simply color them in. But those are, if you're asked to draw the molecular orbitals, these sort of simple pictures would work. And here's another example of some simple pictures, in phase, out of phase. But the reality is, we're probably not going to do that in this class. The online problem sets, I don't think they really have that ability, and on a test it'd be really complicated to expect you to draw these molecular orbitals. You really need, as we'll see in a few minutes, you really need a computer to calculate them for anything more complex than a diatomic molecule. What I would expect you to know is, if I show you a picture of one of these orbitals on an exam, molecular orbitals, I'd expect you to know which molecular orbital that is. Is it a pi star molecular orbital? Is it a pi molecular orbital? Sigma? I would expect you to be able to pick out these patterns, but to actually draw them yourself, I would not expect that. What we will be using more in this class is molecular orbital diagrams. So these show the energy level of the molecular orbitals, and they're similar to atomic orbital diagrams. They show the formation of bonding and anti-bonding orbitals. So the molecular orbital diagram, they also show atomic orbitals from which each molecular orbital is formed. And an important concept in molecular orbital theory is bond order. And this is how you calculate bond order. It's 1/2 times the quantity of the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals. And in molecular orbital theory, bond orders that are greater than 0 indicate that the molecule is stable and theoretically possible. If you have a bond order of 0, that means that the molecule is not stable. If you had a bond order of 0, that would mean that you have equal number of electrons in bonding molecular orbitals and anti-bonding molecular orbitals. So let's look at a molecular orbital diagram. And again, the simplest molecule we can come up with is H2. An important part to realize on a molecular orbital diagram is starting on the outsides, the left and the right, you see that we have the atomic orbital, 1s atomic orbital for each hydrogen that's in the molecule. And we fill that, we add the electron, each hydrogen starts with 1 electron. Now we mix them to form molecular orbitals. And that's what these dashed lines indicate. It indicates that they're mixing. We form we start with 2 atomic orbitals, so we're going to form 2 molecular orbitals. The lower energy molecular orbital is the sigma 1s, so that's the bonding orbital. And the higher energy molecular orbital is the sigma star 1s, the anti-bonding orbital. So these two would be the molecular orbitals of the molecule H2. And we have 2 electrons, 1 from each hydrogen atom. So we need to fill the molecular orbitals with 2 electrons. So by the Aufbau principle, we start with the lowest energy orbital, which would be the sigma bonding orbital. And then by Hund's rule, we add them with their spins paired. So this would be the final molecular orbital for H2. And the bond order would be calculated as 1/2 2 minus 0, because we have 2 bonding electrons, no anti-bonding electrons. So we'd get a bond order of 1. Now, electrons, again, they're placed in molecular orbitals just like they are in atomic orbitals. So you go from lowest energy to higher energy. And a molecular orbital, just like an atomic orbital, can hold a maximum of 2 electrons, and they have to have opposite spins. Orbitals of equal energy are half filled until you run out of orbitals, and then you start pairing the spins. And again, that's Hund's rule. And we'll see some examples of this. Molecular electron configuration shows the type of molecular orbital and the number of electrons each contains. So you can write these shorthand. So for H2, the configuration would be sigma 1s 2. So this is just like writing an electron configuration like we did in chapter 8 for an atom, but now we can write a molecular orbital electron configuration. So for instance, hydrogen atom would be 1s1, but an H2 molecule would be sigma 1s2. Now let's look at bond order with respect to stability. We've seen the molecular orbital diagram for H2. We've calculated the bond order. We know that's 1. It's a stable molecule. Now if we looked at helium-2, Helium-2 has the same molecular orbitals because, again, we're just mixing two 1s atomic orbitals. But each helium has 2 electrons, so we're going to have a total of 4 electrons to fill in our molecular orbitals. And we would fill them as 1, 2, 3, 4. Now you notice we have the same number of electrons in bonding orbitals that we do in anti-bonding orbitals, so the bond order would be 0. And this is not stable. And helium-2 does not form. And we can also write out its molecular orbital conformation, and that's shown here below. Sigma 1s2, sigma 1s star 2. And that means there are 2 electrons in the sigma orbital and 2 electrons in the sigma star orbital. So let's look at diatomic molecules of the second row. So continue on with lithium. Now we're only showing the 2s orbitals because the 1s orbitals, if you could also show those as well, but they're just going to look like helium-2. You're going to have the sigma 1s and the sigma star 1s, and they're both going to be filled. So now it's really more important to look at the second principal quantum number. Just consider the valence electrons. So lithium-2 looks an awful lot like H2. It has a bond order of 1. It's a stable molecule. When we look at beryllium-2, this looks a lot like helium-2. Right? It has the same number of electrons in anti-bonding orbitals that it does in bonding orbitals. So its bond order is 0. It's not stable. If we continue on, this is where it gets more complicated. We have the 2s atomic orbitals mixing, but now we have the 2p orbitals mixing as well. So each atom has 3 p orbitals, so when they mix, we're going to have to form a total of 6 molecular orbitals. And these are the patterns that they form. So you don't have to necessarily know why these patterns form the way they do. You just have to sort of memorize it. And for boron, carbon, and nitrogen, the pattern goes sigma 2s, sigma star 2s, pi 2p, sigma 2p, pi star 2p, sigma star 2p. And this is what's known as with sp mixing. Now from nitrogen to the right in the periodic table, so for oxygen, fluorine, and neon, you don't have sp mixing, so the pattern changes. You have sigma 2s, sigma star 2s, that's the same, but here's where the change occurs. The next orbital, the next lowest energy orbital would be sigma 2p followed by pi 2p. So these are reversed. And then the top is the same, pi star 2p and sigma star 2p. So it's important that you remember these patterns. If we look at the second row up to N2, so these are all the atoms that would have sp mixing. This is what we would see for the diatomic molecules that they form. So lithium-2, like we saw, bond order is going to be 1. Beryllium-2, bond order is 0. It doesn't exist. What about boron-2? We add, again, 2 more electrons in our molecular orbitals, but now they're added to the pi 2p orbital. So they have to add, following Hund's rule, as the spins are going to be unpaired. And what does that mean? There's unpaired electrons. That means that this is a paramagnetic molecule. This should be magnetic. Carbon 2, we add 2 more, and now we see we have a diamagnetic molecule. The spins are both paired now. And the bond order for carbon 2 would be 2. And nitrogen 2, again, we add 2 more electrons, and they fit into the sigma bonding orbital, and we get a bond order of 3. So molecular orbital theory predicts both magnetic properties and the stability of diatomic molecules. So by the bond order, we can tell if a molecule is going to be stable, and by the number, the presence or absence of unpaired electrons, we could tell if it's paramagnetic or diamagnetic. Now we switch the pattern from oxygen to neon, so we don't have what's known as sp mixing. And we see that O2, when we add our electrons, so 6 from each oxygen, so we'd add a total of 12, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we see that we have unpaired electrons. The bond order is 2, so it's stable molecule, but we have unpaired electrons, so it should be magnetic. F2, we add 2 more, and they're going into anti-bonding orbitals, so the bond order is going to decrease. And finally, neon 2, we see that we have the same number of electrons in anti-bonding orbitals that we do in bonding orbitals, so the bond order is going to be 0, and it's non-existent. And here's just a picture used by your book to show that oxygen is in fact magnetic. Here we have liquid oxygen being caught in the poles of a magnet. And hopefully I'll try to show you a video of this in class. And if you're curious as to why there's a change in the pattern between nitrogen and oxygen, I found this figure to help explain it. And it really shows that the sigma 2p orbital, as you move across the periodic table, its energy level is changing. So its energy level is really decreasing as you move across the periodic table. So there must be some effect of effective nuclear charge that's making this 2p orbital lower in energy relative to the other molecular orbitals. And then between nitrogen and oxygen is where you get this crossover point. Again, in this class, don't be concerned. You don't really need to be concerned why this happens. You just have to remember the pattern. Figure 1122 is a good summary. And it shows you some examples with sp mixing and without. It shows you their electron configurations. So if you're comfortable with drawing these orbitals out and filling them in, this would be a very good starting point to look, a review, if you will. Just be comfortable with these diatomic molecules. They're making their molecular orbitals and filling them. And one thing that's also interesting to note is you see that the bond order is increasing up till N2, and then it decreases. And that's sort of the same pattern you see with bond energy. The bond energy increases and then decreases. And when we talked about bonding in chapter 9, we know that the energy and the bond length are inversely related. So the lower the bond energy, the higher the bond length. So the bond length is decreasing to N2, and then it increases from there on out. I'm going to bring up two important terms that I don't believe your book really talks about, but I feel they're important, and they're really important when you go on to organic chemistry. And that's the concept of HOMO and LUMO. So what do those stand for? LUMO stands for the lowest unoccupied molecular orbital. And if we look at an example of N2, what is the lowest energy unoccupied molecular orbital? That would be this one, which is the pi star 2p. HOMO stands for highest occupied molecular orbital. So the highest energy orbital that has electrons would be pi 2p. Now, why are these terms important? Well, these orbitals are the ones that are generally involved in chemistry and in spectroscopy. So the electrons down here, they're very low energy, and they really aren't going to interact. They're very stable. So you're going to get, when molecules are reacting with one another, or they're absorbing energy, that's going to happen up here in the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And these are also called frontier orbitals. So if you ever hear of frontier orbital or frontier orbital theory when you take organic chemistry, just remember that this is what that is referring to. Right. So we've looked at diatomic molecules. What if we looked at some diatomic ions? We saw that helium-2 has a bond order of 0. What if we had helium-2 plus? So that's a helium-2 molecule with one less electron. So by molecular orbital theory, helium-2 plus has a bond order of 0.5, so it's theoretically possible. So this really indicates that you can have crazy, it's a pretty crazy molecule, right? Helium's a noble gas. You wouldn't think that it would be able to create a molecule, bond with another atom. It's not like xenon that's farther down the periodic table that can have an expanded valence. But according to molecular orbital theory, it can. So let's try another practice question. Again, this one is taken from your book, Sample Problem 11.3. Now, use molecular orbital diagrams to find bond orders and predict whether H2 plus and H2 minus exist. And if either of them exists, write out the electron configuration. All right, and for a solution, let's look at this. H2 plus has 1 electron, while H2 minus has 3 electrons to place. So the first step would be to draw out our molecular orbitals. So let's do that. So each hydrogen is going to come with a 1s orbital. These will mix and we will form the sigma 1s and the sigma star 1s. So the bonding molecular orbital and the anti-bonding molecular orbital. Normally, each hydrogen will have one electron each. But now let's just consider the ions. So H2 plus is only going to have one electron because we have a positive charge, so we have to take away one electron. So only one electron to place. It goes into the sigma orbital. What is the bond order? That would be 1/2 times 1 minus 0. We have one bonding electron, no anti-bonding electrons. So we get a bond order of 0.5. So theoretically, that would be possible. And its electron configuration then would become sigma 1s 1. Now if we look at H2 minus, H2 minus is going to have 3 electrons. Okay, so the bond order again is going to be 0.5. We have 2 bonding electrons, 1 anti-bonding, so that again becomes 1/2 times 1, which equals 0.5. And now its electron configuration would be sigma 1s 1, sigma star 1s, sigma 1s 2, sigma star 1s 1. Okay, practice question 6. Use molecular orbital theory to predict the potential existence of neon 2 and or neon 2 plus. I think if you remember, we've already looked at neon 2, but what about neon 2 plus? Okay, first step, we need to draw out our molecular orbital diagram. So each neon will have one 2s orbital. I'll draw that a little bit higher up. One 2s orbital and 3 2p orbitals. So these mix. You get a sigma 1s, sigma 2s, sigma star 2s. Now you have to remember that neon has no sp mixing. So we're going to get sigma 2p, pi 2p, pi star 2p, and sigma star 2p. So this is the pattern that we have to follow for our molecular orbitals. And I'll rewrite them so they're just easier to see. Sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. Okay, so neon, each neon, 1, 2, 3, 4, 5, 6, 7, 8. So each neon is going to come with 8 electrons. So 8 plus 8 would be 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we see that Neon 2, we don't really need to calculate the bond order because we can see that there's equal numbers of electrons in anti-bonding and bonding orbitals, so its bond order is going to be 0. It doesn't exist. But if we looked at Neon 2 plus, that would be 1 less electron. So let's look at that bond order. It's going to be 1/2. How many bonding electrons do we have? We have 2 in the sigma 2s, 2 more in the sigma 2p, and 4 in the pi 2p. So that would be a total of 8. Now if we look at anti-bonding, we have 1, 2, 3, 4, 5, 6, 7. Only 7. So we get a bond order of 0.5. So theoretically, Neon 2 plus can exist. So our correct choice, our correct multiple choice answer would be D. Neon 2 is not going to exist. Neon 2 plus may exist. If we look at the configuration of some other ions, we see that lithium 2 possible. Beryllium 2 plus is also possible. Remember, beryllium 2 wasn't possible. And you go to these diatomic cations formed with the second row, you can see that they're all theoretically possible. So that brings up another type of question we can ask. Is a cation or an anion, are they more stable than the uncharged species? Are they less stable? Are their bonds longer or shorter? Are their bonds stronger or weaker? So here's a practice question. Use molecular orbital theory to select the correct statement below. Okay, let's look at question or statement A. C2 minus has a longer bond length than C2 plus. Down here we see the molecular orbital diagram for C2. If we had C2 minus, we would add 1 electron. C2 plus, we would remove 1 electron. So you can, if you wanted to, you could do both of those things and then calculate the bond order and see which had a higher bond order. The higher bond order means the shorter bond. The lower bond order would be a longer bond. But you could just realize that for C2 minus, you're adding 1 electron in a bonding orbital. So by adding more electrons in bonding orbitals, you're going to increase the bond order, which in turn decreases the bond length. So C2 minus would actually have a shorter bond than C2 plus. And C2 plus, you're removing a bonding electron, so that in turn is going to lower the bond order and lengthen the bond length. All right, what about statement 2? O2 minus is unstable. Okay, so we can take the molecular orbital diagram for O2, and O2 minus, we would add 1 electron. Now for a species to be unstable, they would have to have a bond order of 0. And we can see there are more electrons in bonding orbitals than they are in anti-bonding orbitals. So that statement is incorrect. But if you wanted to just make sure, you could calculate the bond order. So that would be 1/2 times 8 minus 5. You'd actually get a bond order of 1.5. So it is still a stable species. Finally, process of elimination would say that the last statement is correct. But let's look at it. NO has a bond order of 2.5. And so this is a little bit trickier to answer, right? Because all the molecular orbitals we've looked at so far are for diatomic, homodiatomic molecules. We haven't looked at a molecule that has two different atoms in it. But let's just use, for sake of argument, let's use the pattern here from O2. So we have sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. And then if we had nitrogen and oxygen, we're going to have 5 valence electrons from nitrogen and 6 electrons from oxygen. So we're going to have a total of 11 electrons to fill. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's calculate the bond order for this. How many bonding electrons do we have? There's 2 in the sigma 2s, 2 in the sigma 2p, and 4 in the pi 2p. So that would be 8. How many anti-bonding? We have 2 in the pi star 2p and 1 in the pi star 2p. So that's 3. So 1/2 of 8 minus 3 equals 2.5. So that is a correct statement. And what if you didn't know that the pattern for NO followed the same as O2? Well, if you used the molecular orbital pattern for N2, you would actually get the same answer for NO. And we're going to see an example of NO here in a minute. We're going to talk a little bit more about this. So let's try another practice question. Use molecular orbital theory to explain bond properties. And this is sample problem 11.4 in your book. So explain the following data with diagrams showing the occupancy of the molecular orbitals. So you see that N2 has a bond energy of 945, N2 plus has a lower bond energy, and bond length, N2 has a shorter bond than N2 plus. In contrast, O2 has a weaker bond than O2 plus and a longer bond than O2 plus. So if we used molecular orbitals, this would be for the N2 and the N2 plus. So N2 has a bond order of 1/2 times 8 minus 2. So that would be a bond order of 3. Now N2 plus, we remove one of those electrons, and that's coming out of the sigma 2p bonding orbital. So that would change our bond order calculation to 7 minus 2, which would be a bond order of 2.5. So N2 plus is actually going to be a weaker bond than N2, and therefore it's going to be a longer bond. Now let's write the diagram for oxygen. And note that the pattern changes. So oxygen each has 6 valence electrons. We need a total of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. The bond order for O2 becomes 1/2 of 8 minus 1, 2, 3, 4. So that would be a bond order of 2. Now for O2 plus, we remove 1 electron, but that's coming out of an anti-bonding orbital. So that becomes 8 minus 3, and the bond order then is 2.5. So we see that O2, in this case, has the lowest bond order of all 4 of these species. So it has the lowest bond energy and the highest bond length. N2 plus and O2 plus both have the same bond order, and so you can see that they both have a similar bond length. Their bond strength is not quite the same, the bond energy, so you can't directly compare them in that sense. But if you compare the bond energy of O2 and O2 plus, or N2 and N2 plus, you see that the higher bond order species has a higher bond energy. Right. And we touched on this a little in the 7th practice question, but you can actually write molecular orbitals for heteroatomic molecules. And the pattern here is shown for NO. And this actually follows the same pattern as you would for N2, where you have the pi 2p lower energy than the sigma 2p. I've seen it the other way as well. So I think there's really, the energy levels are really close, and I think it would be accurate to show it the opposite way as well. What you should know when you're trying to make form molecular orbitals with a heteroatomic molecule, the effective nuclear charge is going to alter the diagram, and what that means is atomic orbitals for more electronegative atom are going to be lower in energy. So we see that here. The 2s orbital, atomic orbital for oxygen is lower in energy than the 2s orbital for nitrogen. So this atomic orbital on oxygen is going to be closer in energy to the bonding molecular orbital, and the atomic orbital on nitrogen is going to be closer in energy to the anti-bonding molecular orbital. So molecular orbital theory, as we've seen for NO, predicts that this electron, this unpaired electron, is going to be closer to nitrogen because the atomic orbitals for nitrogen are higher in energy than the orbitals for oxygen. It's less electronegative. Do we have any proof of that? Well, I mentioned this molecule last time. We see that there's this NO group. That's a good indication that it could have an unpaired electron. Now, when you put this unpaired electron into a magnetic field, you can have a change in energy between plus 1/2 and minus 1/2 spin states. Now, nitrogen also has a nuclear magnetic field. So the nucleus of nitrogen can actually split that spin state more, 3 times more to be exact. And when you look at the EPR spectrum of this molecule, you see that there are 3 absorption lines. And that indicates that, yes, that unpaired electron is really spending more time on the nitrogen because it's being split into 3 absorption lines by that nucleus. And if it was on the oxygen, you would not see that the same pattern. And this is, again, direct evidence supporting molecular orbital theory. If we look at another heteroatomic molecule, and that's for HF, you see that the difference in the molecular orbitals for HF, or excuse me, the atomic orbitals, fluorine is so electronegative that its atomic orbitals are much, much lower in energy. Here we see the 2p orbitals, and for hydrogen, the 1s orbital is way up here. So we get an interaction of 2p fluorine atomic orbitals and 1s atomic orbital from hydrogen. And that can only make, it's only good to mix with one of the p orbitals, so you get a sigma and a sigma star, and the other 2 unhybridized, you can think of them, non-mixing p orbitals from fluorine, turn into what is called non-bonding molecular orbitals. In other classes, you might really start talking more about these non-bonding molecular orbitals. We're not going to, in this class, I'm not going to expect you to know about non-bonding molecular orbitals. And you can do molecular orbital theory. You can make molecular orbitals on larger orbitals, and it becomes really challenging. So you use equations like this, and you do what's called linear combinations of atomic orbitals. You really need a computer program to do this. And there's certain programs like Spartan. You might use Spartan in future classes. And what you get for some of these looks like this. Your book shows you the picture of benzene, where you have these big molecular orbitals that are spread out over the entire molecule. Here's an example of some molecular orbitals for water. And even water, having 3 atoms, you see just how complex it can get. And this, again, really explains why you see the molecular absorption spectra that you do. And I'm going to talk a little bit more about this in detail, using an even more complex molecule, FAD. And this is used in your cells. A lot of your proteins use this as a cofactor to transfer electrons. So this molecule can accept an electron. Actually, it can accept up to 2 electrons. But some people have actually studied the molecular orbitals of this molecule, and here are just a few of them that are shown. And if you look down here, you see that they correspond to the 60th, 62nd, 70th. So there's just hundreds of molecular orbitals for a molecule this complex. And again, you would really need a computer to do this. You could not do this in your head. So how does that relate to molecular absorption spectra? Well, if we look back here, let's go back to water. So for water, you can see that just like an atomic spectra, you can have absorption of light And what that would do is it would bump one of those electrons, in this case it'd be a non-bonding electron, up into a higher energy molecular orbital. And that would be shown like here as an absorption. So FAD is the same story. One of these molecular orbitals, the HOMO, highest occupied molecular orbital, can absorb energy and bump an electron up into the LUMO, per se. So if we look at the FAD, this black line, this spectrum comes from the FAD in a protein known as ETF, electron transferring flavoprotein. You see that this black line is the molecular absorption spectra for this protein. And for in particular, it's for the FAD cofactor. If this protein did not include the FAD cofactor, it would not be absorbing light in this region. And this is in the blue visible region, and this actually makes the protein a sort of a yellow color. But now when we add one electron to that FAD, the absorption spectra changes. So as we're adding electrons to the FAD in this protein, the peak at 375 nanometers is increasing, and the peak at 436 nanometers decreases. And why is that? It's because by adding that electron, you're adding it goes into the LUMO, the lowest unoccupied molecular orbital, and thus you're changing the energy levels that are available for an absorption. Now here's an important figure, especially if you were going on to study organic chemistry in more detail. Here's some relative energy levels of molecular orbital absorptions. So the lowest energy absorption you can get is N, which is a non-bonding pair of electrons, to the pi star molecular orbital. And then there's also N to sigma star and pi to pi star. Both of these are very similar in energy. An N to pi star would usually be in the visible range. N to sigma star, pi to pi star, those are more ultraviolet. And then the highest energy would be a sigma to a sigma star, and that's much higher in energy. The other use when we talk about molecular orbital theory, another way of using molecular orbital theory to explain natural phenomenon comes in the aurora borealis. And now we're looking at emission spectra, molecular emission spectra. So electrons that are in excited states relaxing down to lower energy molecular orbitals. And this figure is from a different text, but it shows you the colors in the aurora and which chemical species they're caused by, and the exact wavelength that those occur at. So an N2 star, that indicates that the N2 molecule is excited. They're responsible for deep red, the deep red color in aurora. And you can use the molecular orbital diagrams to show just why this can occur. So if you have N2 star, that means it's in an excited state. So what does that mean? That means one electron went from the HOMO to the LUMO. So its electron configuration is shown here. It has two unpaired electrons. When that excited electron relaxes back down, what happens is you get an emission of light that corresponds to the energy difference in those two states, the pi star to the sigma. And in the case of N2, it would be between 650 and 680 nanometers. So N2 plus also can do this. There's one less electron in N2 plus, but the transition's the same. But now you see that the energy level is higher. But again, you have an electron that's in an excited state, and it relaxes down to a lower energy state, and it gives off energy that corresponds to the difference in those two states. In summary, what are some advantages of molecular orbital theory? One, it provides the most complete picture of covalent bonding, including bond types and bond orders. And it accounts for magnetic and spectroscopic properties. A disadvantage of molecular orbital theory is it's the most difficult to apply. If you're going to try it on larger molecules, it's really impossible unless you use a hardcore simulation program. And another big disadvantage of molecular orbital theory is that it does not account for molecular shape. So you really have to use a number of these theories together to get a full description of molecular shape, molecular bonding, and magnetic and spectroscopic properties. All right, that finishes up Chapter 11. Next lecture, we're going to be dealing with Chapter 4, specifically 4.1 to 4.3, and 4.5 and 4.6. So we're not going to talk about 4.4, which is acid-base chemistry, and I believe there's also another section or two, 4.7, at the end of Chapter 4 that we're not going to touch.